In this lecture, we are going to discuss about polar plot. And from polar plot, we will extend this to the Nyquist criterion and the Nyquist plot. So you can see here a block diagram which contains a controller transfer function GC and a plant transfer function GP connected in series. And in the next block diagram, the G of S is the combined transfer function of GC and GP, which is the forward path transfer function. And the feedback element is H of S. Now, the objective is to find the stability status of the closed loop system from the open loop transfer function, poles and zeros. So let G of S equals E by dg, where ng is the numerator and dg is the denominator expression, and H of S equals nh divided by dh. Then gh equals ng nh divided by dg dh. Now, if we convert this to closed loop transfer function, we know that it is g by 1 plus gh. Gh can be replaced by this expression ng nh by dg dh, and g can be replaced by ng by dg. So after simplification, what we get is ng dh divided by dg dh plus ng nh. Now, so this is a closed loop transfer function, and the denominator when equated to 0 gives the closed loop poles. So dg dh plus ng nh equals 0 will give the closed loop poles. Now let us analyze another expression 1 plus gh, which is an extension of gh. That is, if we know the expression of gh, we know the open loop poles and open loop zeros. Thus we know the poles and zeros of 1 plus gh, because it's just an extension of gh. So 1 plus gh equals dg dh plus ng nh divided by dg dh. So how will you find the zeros of this 1 plus gh? If the numerator is equated to 0, that is dg dh nh equals 0. And if you solve it, you will get the zeros of 1 plus gh. And you can see that the to get the closed loop poles, you equate the same expression to 0, dg dh plus ng nh. So this gives zeros of 1 plus gh as well as the closed loop poles, or the poles of the closed loop transfer function. That is a relation between 1 plus gh and the closed loop transfer function, 1 plus gh and the closed loop transfer function. Now denominator of gh and 1 plus gh are same, right? Denominator of 1 plus gh is dg dh. Then denominator of gh is dg dh. So basically poles of gh is equal to poles of 1 plus gh, right? So if you know the poles of open loop transfer function, it is equivalent to knowing the poles of 1 plus gh. And if you know the zeros of 1 plus gh, it is equivalent to knowing the poles of the closed loop transfer function. This is what is a concept used in Nyquist criterion, or to draw the Nyquist plot, or rather to draw the polar plot. Now you can see here an S-plane and a W, where mapping of S-plane to W plane can be done using this expression 1 plus gh equals w. That means for any point sigma plus j omega in the S-plane, if you evaluate 1 plus g of sigma plus j omega into h of sigma plus j omega, you will get a corresponding point in the W plane, which is the mapping of S-plane in the W plane, mapping of a point in the S-plane to the W plane. The point sigma plus j omega in S-plane can be mapped to W plane at a different point. Similarly, we really want to map the imaginary axis and the RHP of S-plane completely to the W plane and check whether the origin of W plane is covered or not. If it is covered, the system is unstable, and if it is not covered, the system is stable. Please go through these sentences from this similarly onwards. What does it say? We know that for 1 plus gh equals 0, for the equation 1 plus gh equals 0, if there exists at least one s value in the right half plane, then we say that the system is unstable. Or rather, if we don't have any s value on the RHP of the s plane for which 1 plus gh equals 0, then we say that the system is stable. So here we use the concept in the converse manner. We use it conversely. That means anyway 1 plus gh equals 0 is to be satisfied, right? So this is a 1 plus gh plane. Which one? The W plane is the 1 plus gh plane. So if that encircles origin, that means 1 plus gh equals 0 is satisfied, right? And if we rather than considering a single point on the S plane, if we are taking the complete RHP plus the imaginary axis, then that is the unstable region, right? So for this unstable region, it is this unstable region, if any S point satisfies 1 plus gh equals 0, that is for any S point, if encirclement of origin is satisfied, it happens in the W plane, then we say that the system is unstable. That is what is written here. That is, now I'll repeat these sentences. We really want to map the imaginary axis and RHP of S plane completely to the W plane to check instability, right? So whether origin of W plane is covered or not. If it is covered, the system is unstable, and if it is not covered, the system is stable. So here first we take the whole RHP plus imaginary axis. If any S value is satisfying the condition 1 plus gh equals 0 in the W plane, because 1 plus gh plane is W plane. So if there is an encirclement on the origin, then we say that the system is unstable. So this is what we are going to use in Nyquist criterion. The one-to-one mapping will lead to the mapping of one contour in S plane onto another contour in W plane. We will see, rather than mapping a specific point on S plane to W plane, if we have a contour, you see here we have a contour. This is a contour in S plane. Now we have the 1 plus gh expression as S minus beta 1 into S minus beta 2 into etc. up to S minus beta m whole divided by S minus alpha 1 into S minus alpha 2 into S minus alpha m, suppose. Then this is in the pole 0 form, right? Where beta 1, beta 2, etc. are the zeros, and alpha 1, alpha 2, etc. up to alpha m are the poles. Now we suppose that the points are here: alpha 1, alpha 2, beta 2, and beta 1. And you can see here beta 1 is the only point inside the contour, right? Inside the contour. Now, how will you evaluate the numerator S minus beta 1 into S minus beta 2? This one. Suppose if we give S equals S1. Initially, if you are giving S equals S1. Then, what is a phasor S1 minus beta 1? That is shown here, S1 minus beta 1. This one, the line joining the phasor which joins the points beta 1 and S1. Now S1 minus beta 2, this one, right? S1 minus beta 2. This is S1 minus alpha 1, then S1 minus alpha 2. Now this is only one point on the contour. Now our aim is to cover the complete contour, right? So we move on to the next point S2, right? We move on to the next point S2. So S2 minus beta 1 will be another phasor, right? Then S2 minus beta 2, another phasor, S2 minus alpha 1, S2 minus alpha 2. This is the numerator, right? Numerator of 1 plus gh. So we are multiplying all these, and you are dividing it by S1 minus alpha 1, S1 minus alpha 2, these things. So if we are traversing through the contour in the clockwise direction, your S1, next point is S2, S3, S4, like that you are traversing like this, right? So if the complete contour is traversed, then that means that there is a angle contribution of 2 pi, right? The angle contribution of 2 pi. This is actually minus 2 pi, right? This is in the clockwise direction, so this is minus 2 pi. So what is the angle contributed by each pole and 0? Let us see that. So for all the points outside the contour, what happens is for every upward movement of the phaser also when you traverse through the contour, right? Suppose we are considering the point beta 2, then for S1 minus beta 2 phaser, it moves in the upward direction on this side of the contour, and while moving through the other side of the contour, it is just in the reverse direction, so it cancels the same angle, right? Those angles are cancelled. So basically, if you traverse through the contour completely, then the angle contributed by beta 2 would be 0. Alpha 1 also it would be 0. Similarly for alpha 2 also it would be 0. So basically for any point outside the contour, the contribution of angle when traversing through the contour completely, the contribution of angle would be 0. But what about the point inside the contour? Then this is the phaser, right? Now you are moving to S2, right? S3, S4. So this is basically a clockwise rotation. This phaser rotates clockwise. So there is a 360-degree contribution here, or rather a minus 2 pi contribution, right? Because it's in the clockwise direction. So for any point inside the contour, the contribution is 360-degree, but any point outside the contour, the contribution is 0. Now we see for these points, I'll read these points. Now for a point inside the contour, if it is a 0, will map to a contour in the W plane which encircles in the clockwise direction minus. For a pole inside the contour in S plane, corresponding encirclement in the W plane in the anti-clockwise direction, because pole lies on the denominator of 1 plus gh and contributes to negative of 2 pi, that is plus 2 pi. That means now we have seen that inside the contour, if there is a point, then that maps to a contour in the W plane which encircles in the clockwise direction. And suppose if it is a 0, these phases are S1 minus beta 1, S2 minus beta 2, S3 minus beta S3 minus beta 1, S4 minus beta 1, S5 minus beta 1, like that you are traversing through the contour, right? Now if it is a pole lies in the denominator, so the angle contribution is negative, right? When you find the angle, if it is in the denominator, then it is negative angle, right? The contribution is negative angle. So for any clockwise direction here, for a pole in the corresponding encirclement will be in the opposite direction in the W plane. If it is a 0 in the S plane, then the corresponding encirclement in the W plane will be in the same direction, okay, and in the same direction around the origin, because 1 plus gh equals 0 is our equation, right? This is 1 plus gh plane, and 1 plus gh equals 0 is our equation. So this is the magnitude of W, and this is the phase of the point in the W. This is the point, and we are traversing through this particular contour when we move through this contour in the S plane. So here it is clockwise, here it is anti-clockwise, right? Here it is clockwise, and here also it is clockwise if it is a 0. And if the encirclement is clockwise in the S plane and it is in the opposite direction in the W plane, then it is a pole. The point inside the contour is a pole. So now for a point inside the contour, if it is a 0, will map to a contour in W plane which encircles in the clockwise direction, that is minus 2 pi. For a pole inside the contour in S plane, corresponding encirclement in the W plane is in the anti-clockwise direction, because the pole lies on the denominator of 1 plus gh and contributes to negative of minus 2 pi equals plus 2 pi. So clockwise encirclement in S plane is minus 2 pi, right? So corresponding encirclement in the W plane for 0 is minus 2 pi itself in the same direction. Clockwise encirclement in the S plane is also minus 2 pi, because it's in the clockwise direction, but the corresponding encirclement in the W plane is opposite. So minus of minus 2 pi is plus 2 pi. That is what we have obtained. Now, for a point outside the contour in S-plane, the angle contribution for one encirclement is 0 for the phasor. That we have already seen. For any point outside, when we traverse through the contour, for every upward movement, there is a downward movement. For every positive angle, there is a negative angle. So while traversing throughout the contour, the equivalent contribution will be the total contribution of angle would be 0. Now, if two poles, and with this concept we will see an example. If two poles and 1, 0 are in the contour of S-plane, then what will be the corresponding encirclements in the W plane? Suppose we have a contour here and two poles are shown and 1, 0 is shown, right? So how many encirclements are there in the W plane? For these two, what are the corresponding encirclements in the W plane? Plus 2 pi, right? 2 plus 2 pi are there, right? But there is 1, 0. Correspondingly, we have corresponding to this, we have a minus 2 pi here. So basically 1 plus 2 pi is there, right? Equivalent the total contribution is plus 2 pi. So that means one encirclement around the origin, right? This gives plus 2 pi, this gives plus 2 pi, this gives minus 2 pi. So total is now 1 plus 2 pi. Okay, two poles contributes to minus 2 pi into 2 and one pole contributes to plus 2 pi. So net contribution is one encirclement in the W plane in the anti-clockwise direction, which is minus 2 pi. Now, the contour we are going to enlarge. We are going to consider the contour, this contour as the entire RHP including the imaginary axis. This is what is the contour of interest, right? Because we want to see whether any S value is there inside this particular contour. That means the entire RHP and the imaginary axis for which the 1 plus GH equals 0 is satisfied. That means encirclement around the origin 1 plus GH equals 0 is satisfied. Satisfied, then the system is said to be unstable. So we'll see here. So this is the entire contour. Now we see that P poles of 1 plus GH, and we know that we have already proved that poles of 1 plus GH is similar to poles of GH, right? In the sense the same equation is used to find the poles of GH. So this is already known. If you are given the open loop transfer function, we are going to comment on the closed loop stability. So if GH is known, then the poles of GH are already known. So that means the open loop poles are already known. So suppose if P poles are there and Z zeros are there for 1 plus GH. If Z zeros are there for 1 plus GH, what is the importance of zeros of 1 plus GH? That is a closed loop poles, right? Here we have already seen. Yes, same as zeros of 1 plus GH, right? This gives closed loop poles. DGDH plus NGNH gives closed loop poles. This is similar to DGDH plus NGNH, that is the numerator of 1 plus GH, which gives zeros of 1 plus GH. So basically our aim is to find the zeros of 1 plus GH so that we get the number of closed loop poles on the right half plane, right half plane. So by that we check the stability, we comment on the stability. So now, so how to find the number of counterclockwise encirclements around origin? So when will we get counterclockwise encirclements and when will we get clockwise encirclements? We get clockwise encirclements for zeros. We get counterclockwise encirclements for poles. So number of counterclockwise encirclements around the origin in the W plane can be given by P minus Z, right? If we know the open loop poles and open loop zeros, or zeros of 1 plus GH, then we have P minus Z encirclements, counterclockwise encirclements in the W plane. So now we can state the Nyquist stability criterion. So we can find the right half plane zeros of 1 plus GH, since we already know P. What is P? Open loop poles. P and can calculate N from mapping. So our aim is to find Z. And after mapping, we know the number of counterclockwise encirclements. We know the P from the given function itself. Given function is open loop transfer function. So using P and then if we know Z, then Z is basically closed loop poles. This is our aim. Okay. So zeros in RHP of 1 plus GH is equivalent to number of closed loop poles in RHP. There should not be any encirclements around origin in the W plane for the closed loop system to be stable, because if there is an encirclement, if there is one counterclockwise encirclement, that means for 1 plus GH equals 0, there is at least one S value on the RHP. That means it is unstable. So no encirclement should be there. Net encirclement should be 0 for a stable system. That means Z equals 0. Okay. Since it represents closed loop pole. This is the closed loop pole. Z equals 0. Open loop. So once again, I'll repeat this. There should not be any encirclements around origin in the W plane for the closed loop system to be stable. That is Z equals 0, since it represents closed loop poles. Open loop stable system implies. Now, what about open loop stable system? We are given the open loop system, right? If it is stable, then what does that mean? There are no RHP poles, right? That means P equals 0. No right half plane poles. That means no encirclements in the W plane, right? Now you can see here open loop stable system means P equals 0, which implies the corresponding mapping in the W plane is stable under closed loop operation also, because no encirclements around the origin. Now instead of taking 1 plus GH plane, if we take GH plane, because our function under consideration is GH, right? We started with 1 plus GH to relate the poles and 0. Moving towards GH. So instead of using 1 plus GH, if we are using GH, then corresponding to 1 plus GH equals 0. For GH equals, if we take GH, then GH equals -1, right? So instead of looking at the number of encirclements around origin, now we have to check the number of encirclements around -1 plus J0. If we take the GH plane, instead of taking 1 plus GH plane, if we shift this to GH plane, then instead of checking the number of encirclements around origin, we should check the number of encirclements around -1 plus J0. So now you can see here, now instead of taking 1 plus GH plane, if we take GH plane, then we can check encirclements around -1 plus J0 rather than looking at the encirclements around origin. If Z equals P, that means no encirclements, right? P minus Z, no encirclements. If Z greater than P, then clockwise encirclements, because more zeros, more contribution to clockwise encirclements. If Z less than P, then counterclockwise encirclements. So this is what we are going to get. Now you see here, this is our plane, right? The plane is the contour. The contour, this is called the Nyquist contour. The Nyquist contour has infinite radius, right? Some S we are taking in the polar form, in the exponential form it is R e raised to j theta, right? Where R is tending to infinity because the full RHP we are considering. And what about theta? Theta we can consider like this. With respect to omega, we will consider omega starts from here, right, to here, then it traverses through this particular segment to this point, and it goes to again the origin. So we'll assume like this: it starts from omega equals 0 plus, and it goes to omega equals plus infinity, then from plus infinity to minus infinity, and to omega equals 0 minus. So what we are going to do is, we are initially drawing the plot for omega equals 0 plus to omega equals plus infinity. Okay, omega equals 0 plus to omega equals plus infinity. Now, but actually we need to get this also, 0 minus to minus infinity also we need to get. So instead of drawing the complete plot, what we are going to do is, initially we are drawing 0 plus to plus infinity, and we are taking the mirror image also, and we combine both. So then we will get the full plot. That is what we are going to do. We'll see that. I'm just mentioning it here, that's all. So now theta varies from plus 90 degree to minus 90 degree. What is the variation of theta? This line corresponds to plus 90 degree, right? Plus 90 degree. Then this is minus 90 degree, right? This is minus 90 degree. So plus 90 degree to minus 90 degree. Omega variation is from 0 plus to plus infinity to minus infinity to 0 minus. Okay, this is the variation omega. This is the variation of theta. Normally for GH equals some numerator function divided by a denominator function, power of numerator function is less than power of denominator function. Normally this is what happens. So m less than n. Okay, m less than n. Now in this case, for s equals r e raised to j theta, for r tends to infinity, it maps to origin. Why is it so? Because m less than n, right? M less than n in the sense the power of numerator is less than power of denominator. That means the zeros have more power when compared to poles of the open loop transfer function, right? So what will happen? We are assuming r tends to infinity. When r is tending to infinity, what happens in the w plane? It is tending to origin because it will be like 1 by infinity, right? So 1 by infinity will be tending to 0. Okay, that is what is happening. Now if m equals n, the entire semicircle maps to a constant, right? The entire semicircle maps to a constant. Mapping of the entire contour, how will you map the entire contour? Omega equals 0 plus 2 plus infinity to omega equals minus infinity to 0 minus. So initially we will draw for this omega equals 0 plus 2 plus infinity, and we will take the mirror image, so we will get this also, and to get the entire contour we combine both. Now, what is the Nyquist criterion? The criterion says if n is the number of counterclockwise encirclements in the GH plane. Now we have shifted from 1 plus GH plane to GH plane. This is the plane under consideration, the open loop transfer function plane, the open loop plane. Okay, which is mapped from the S plane. Then n equals p minus z, where p is the number of open loop poles enclosed by the Nyquist region in S plane, and z is the number of zeros. Number of zeros in the sense which is equal to number of closed loop poles, right? Number of zeros is equal to number of closed loop poles. Normally p equals 0, since we mostly with open loop stable system. We know that for open loop stable system p is 0. There are no right half plane poles in the open loop for the open loop transfer function. Okay. Now we will see the procedure of procedure for drawing the Nyquist plot, and the purpose of Nyquist plot in the next lecture. Okay, let us take a break and we'll continue in the next lecture. Thank you.